All right, we are ready to start. Hi, everybody. I'm Marco Gabordi from Boston University, and this is the second session on semantics. We will have three talks in this session. The first talk will be given by Vikraman, and it will be on symmetries in reversible programming.
All right. Hello. Sound all right? Hello. Hi. I'm Vikraman, and I'm going to be presenting our paper, Symmetries in Reversible Programming. Our paper has a subtitle from Symmetric Rig Groupoids to Reversible Programming Languages, and this work is establishing an algebraic correspondence between a certain class of reversible programming languages and symmetric Rig groupoids. My co-authors are Jacek Karwowski and Sabry. And with that, I'll start the presentation. So what exactly are reversible programs? Well, the easiest way of thinking about them is as permutations. So let me start by giving you two examples of programs, P1 and P2. They operate on this three-element set ABC, and I'm going to draw them as tree transformations. So the first program, P1, performs three operations on this tree ABC. First, it associates to the left using this combinator called assoc_L. And then it applies a swap on the whole tree, moving from A plus B plus C to C plus A plus B associated to the right. And then the third step performs a swap on the bottom leaves of the tree, and that becomes CBA. So this is P1, and P2 does the same thing, but it takes 5 steps. So it does a swap on the bottom right leaves B and C, making it ACB, then does a left rotation, again does a swap on the left children, then does a right rotation, and then again a swap. So it did a lot of operations, but ultimately both P1 and P2 compute the same permutation. Okay, so why are these combinators interesting? Well, they can be organized into this tiny reversible language called pi. So this language has types. We are going to have all the finite types given by 0, 1, plus, and times. And these have the values which are the simplest ones, like 1 has the truth value TT and left and right injections and tuples. And then there's this special kind of program types, which given two types A and B, we write the type A left right arrow suffix 1B, which is the type of one combinators between A and B. So these programs are names for isomorphisms that we can write between these types. We have the obvious one, which is the identity function, and then we have units, which, for example, 0 is the unit for A for the plus, and then we can associate them from left to right, and also we can swap them. For example, A plus B goes to B plus A. The same set of combinators works on products. So 1 is the unit for the product, and we can swap them and associate them. And finally, there's a distributive combinator, which lets us distribute the products over the plus. So these are the primitive combinators, and we can write programs using them by combining them. So there are 3 kinds of composition. For example, at the bottom, you can see that you can compose 2 combinators, C1, C2, sequentially, or you can combine them in parallel using both the plus and the types. Okay. This class of languages were invented by Sabry and his collaborators over the last decade, and there has been a lot of research on the syntax of this language and what you can do with them. For example, as we've heard about quantum computing quite a lot in the keynote and in earlier sessions, Toffoli gates, Hadamard gates, and other reversible Boolean circuits can be expressed in this language. For example, here I'm showing you a controlled combinator which takes a combinator C and does a conditional application on the left. So if I have a combinator which swaps which is Boolean, and then I can apply the controlled combinator to it to get a C0 gate, and apply controlled again to get a 3-bit Toffoli gate. So lots of useful reversible Boolean circuits.
Is the sound getting through? Can you hear us? They can hear us. So I suggest you start again.
Like from the beginning? Or? Like okay, sure, yes. Okay, should I? Yeah, all right, okay. Okay, so getting back to the original problem, we have these programs P1 and P2, and we want to find a equational theory for this language, which lets us decide program equivalence syntactically. And we want to show that these are sound and complete. Okay, so how do you design an equational theory for this combinator language? Well, we'll write a judgment which says that if we have two combinators C1 and C2 between the same types, we can judge whether they are equal. And it turns out, just like the lambda calculus is very simple. It has beta eta equations, but this language has so many combinators. There are lots of equations. So I'll give you an example of some of these. I'll give you some examples of these two combinators. So for example, you can compose two combinators, but this composition has to be associative. So you need a coherence condition for the associativity of composition. You need units for the composition, and then you can invert these combinators. So you need something like groupoid laws, and then you need something like naturality conditions, for example, swap commutes with the type constructors. And also you need some other complicated coherence conditions like pentagon and hexagon. And also these two combinators can be composed in different ways. So it turns out that these equations correspond to coherence conditions of symmetric Rig groupoids, and that is what we will establish in this work. So going back to the original example, let's see how one might equate these programs P1 and P2. So I can tell you exactly this is the equation which shows that P1 and P2 are equal. Well, it's very hard to visualize them, but you can draw a diagram and consider a commuting diagram like this, which uses a hexagon on the left and a naturality on the right to show that they're equal. Okay, so the goal here is so knowing that two programs are equal, how do we generate these equations? Okay, to do this, we are going to design a denotational semantics for pi. To do this denotational semantics, we are going to think about groupoids. So what are groupoids? Groupoids are, you have objects and you have arrows between them which are invertible. So take this program pi, which has types and programs and equations, and notice that all the programs are invertible and the equations are, of course, invertible. And on the right, we have finite sets and bijections between them. And bijections are the invertible morphisms. And in between these bijections, we have two cells, which are the homotopies between them. Homotopies tell you when two functions are extensionally equal. So the goal is to establish correspondence between these two groupoids, and we're going to show that there is a symmetric Rig equivalence between these two. Okay, turns out it's a very hard question. So we cannot do this in one step, and we are going to construct this equivalence in different steps. So the first step is, well, okay, so this language pi is complicated. It has lots of equations. What we are going to do is reduce this language by doing something called strictification. So we have too many types and too many type constructors and lots of syntactic constructs. We're going to reduce this. So think of this like so we've got a big language, and we want to design a smaller language which has the same expressive power as the bigger language. So the first step, I'm going to get rid of the times. So let's take, for example, I want to, if I write down the type bool times bool times bool, it just indicates it has 8 elements. Well, okay, this I can implement multiplication as repeated addition, and I can just write 2 plus 2 plus 2 plus 2. So in this pi plus language, we only have, on the types, we only have sums, okay? And what happens to the combinators? Well, we have all these swap and associativity and other things for both the monadal structures. But once we translate to just plus, the times can be converted to just plus. So we have swaps and assocs and units and other things, but only for the plus. So it turns out that we have to be clever about how we encode this, but we can show that this is actually an equivalence. So we can produce a smaller language with only plus, which has the same expressive power. And then one more step where we, so so this is encoding the number 8, 2 plus 2 plus 2 plus 2, but 8 we can just simply write as successor applied to 0 8 times, so the unary natural numbers. So we can go one more step where we get this other language pi hat, which only allows unary natural numbers for types. And it turns out that the only swaps you need are when you have two adjacent transpositions, which is like successor. When you only have adjacent transpositions, so you have like successor of successor, and we can swap the two. So again, this translation is an equivalence, and the main proposition is that we can go from this language pi to pi plus to pi hat while maintaining all the expressive power that we had in pi. Okay, so we've reduced the number of equations, but we still need to decide when two programs are equal. So now we're going to visualize these programs in pi hat, which only have adjacent transpositions. So going back to our original example, we had P1 and P2. If we think about what the actual content of these permutations is, we can see that P1 only does 1, 2, 3, 4 different transpositions, and we can write them as just lists, where the transpositions are happening. So P1 is this list, and P2 is this list, and we can visualize them as these braid diagrams. What's the advantage of thinking about braid diagrams? Well, braid diagrams have a decidable equational theory. This comes from the theory of group presentations, where these relations between string diagrams can be used to generate symmetric groups, and symmetric groups give us all the permutations. So let me explain what the three relations are. So cancel says that if you have two transpositions next to each other, they cancel. Swap says that if I have a swap somewhere on the left and somewhere on the right, I can move them up and down. And then there's the braid relation, which says that, well, if you have these transpositions and there's a wire you can slide underneath freely, then you can do that and reduce the number of swaps. Okay, so the trick is to use these relations to build a rewriting system. So we have to tweak them a little bit, but we can get a confluent and terminating rewriting system. And out of this rewriting system, what we get is a unique way to decide normal forms for these words in the group. So we get this function nf, which takes a word in the symmetric group and gives us normal form. Okay, and once we have this normal form, we can decide equivalence of two different words. So going back to the example with P1 and P2, they both reduce to this same normal form 0, 1, 0. Okay. Okay. So we've produced this normal form, and now we need to go to the right-hand side of our semantics, which is the groupoid of finite sets and bijections. So how do we go from these normal forms to bijections? Well, we're going to use some tricks with permutations and the representations. So consider the word 0, 1, 0, which says exactly how to map ABC into CBA. So 0 says that we perform a transposition on the 0th position. So map AB to BA, and then 1 says, okay, map the second, swap the second and third, so it becomes BCA, and then again 0, so swap the B and C, we get CBA. Okay, so this 0, 1, 0 can then be translated to something called a lemma code. What is a lemma code? Well, a lemma code is a compact representation of what a permutation does. So the lemma code for this is 0, 1, 2. What does this mean? It says how many inversions you need to perform on the elements. So when you see A, B, C, so how many inversions on A? Well, 0, so don't do anything. Then we hit B, so how many inversions on B? We have to do 1. So there's only one thing which is smaller than B, so we move B one position left, and then two inversions on C, which means map C 2 positions left. So this is the trick which lets us get back to producing a permutation. So all this seems like very low-level combinatorial tricks, but what the main result is that we can actually take any permutation in this language pi hat, and we can keep on extending this equivalence and get back to permutations. And using this entire trick, we can finish this correspondence between pi and the groupoid of finite sets and bijections. Okay, so this is the main result, and what are the implications of this result? Well, the first thing is that we've produced a correspondence between a syntactic thing, which is this language of combinators, and a semantic thing, which is this groupoid of finite sets and bijections. So just like, so in programming languages, there's the Curry-Howard correspondence, but this Curry-Howard correspondence can also be extended to a Lambek correspondence, which establishes a correspondence with algebraic structures. For example, the simply typed Lambek calculus corresponds to Cartesian closed categories, and here we're showing that reversible programming languages correspond to symmetric groupoids. Using this correspondence, we can answer some difficult questions about the semantics of these languages. So in particular, we show that this denotational semantics is adequate and fully abstract with respect to the operational semantics. Since we have a complete semantics, what we can also do is run the semantics and find out what the normal form for a function, for a reversible program is. So we can do normalization by evaluation for reversible circuits. And this also gives us a decision procedure for deciding whether two reversible circuits are equivalent, but just by comparing the normal forms. Another application is that we can take any reversible circuit and write down its truth table as a permutation and get back a program which expresses the same permutation. And finally, there are lots of different representations of reversible circuits that we have in the semantics, and we can. And it turns out that sometimes it's easier to prove theorems about a particular presentation and transfer it to a theorem about the syntax. The nice thing about this is that although there's a lot of proofs in there, it's formalized in constructive type theory using a proof assistant, so you can actually run the semantics and compute things with it. And all of this is available on GitHub and in our artifact. Finally, I just want to point out that this language pi, we took a very small subset of it, but you might have gone to the previous talks where people discussed various extensions to it, and this semantics could possibly be extended to other things. We also get a normalization algorithm out of this semantics, and this is a new way of thinking about how to decide equivalence of reversible Boolean circuits, and it would be interesting to study the efficiency and complexity of this normalization algorithm. The construction of these symmetric monadal structures are the kind of this kind of trick with groupoids and combinatorics is interesting and has other applications to linear logic and combinatorial species and other things. Yeah, with that, I think I'll end the talk, and this is the link to the paper where you can read about all of these things in much more detail. Thank you.
Thank you, Vikraman, for the talk. Despite the technical issues, I will try to keep the question and answer session a bit shorter because we have two other talks. But let's start with questions in the audience.
Yeah, just a super simple, quick question. For the homotopies between bijections, those are unique, right?
Yeah,
because we're working with finite sets. Yeah,
there's at most 1, 2 cells between.
Yeah, just double check.
Yeah.
Any other question in the room? Or any other question online? All right, we have a question online. Can we display it? I remember reading in a text by Loweir that the category of finite set and bijection is the free symmetric monadal category of one generator without proof. Is this a Fermat moment where the proof turned out to be a lot more involved?
Yes, exactly. So yeah, it's a folklore theorem that the free symmetric Rig groupoid on 0 generators is equivalent to the free symmetric monadal groupoid on 1 generator, and all of this is finite sets and bijections, but no one had a proof, and we spent a lot of time trying to finish this proof, and that's what led. I mean, we had a motivation to finish it, which is to do this, and it's a lot more involved than it really is, and especially if you work in a proof system and you work constructively in a proof relevant setting, it's a lot harder to actually produce the proof. So that's why, yeah. So that's an important contribution of this work to produce this proof. Yes.
All right. Thanks. Is there any other question in the room? I don't see any other question online. So let's thank again Vikraman.
Right. Thank you.